Welcome back, folks, to the fourth installment of the topic on NMR. And today we would like to get into spin echoes, which play such an important role in MRI as well. So what is up with spin echoes? What are they? How do we produce them? We said before that the initial signal after a pi/2 pulse is the FID, and that signal decays due to a dephasing of the individual spins. So the spins will precess in the XY plane, but they will not precess at exactly the same angular speed. Why not? Because the magnetic field that spins in different parts of the sample experience is not identical. And since the magnetic field is not identical, then the omega is not going to be identical. And so over time, the individual spins or the individual mu's, the magnetic dipole moments, the individual mu's, they do come out of phase with one another. And so eventually they will not all line up in the same direction to produce the macroscopic signal, the macroscopic magnetization vector. Okay, and at that point, then we lose the signal. So here again is this process in sort of a cartoon picture. Initially, we have every single mu pointing along the strong magnetic field axis, B naught, the z-axis. Then we come in with a pi/2 pulse. And that then has the effect of tilting all these spins into the XY plane, as shown, where they now start precessing about the z-axis. We said that some of them will get ahead and some of them will lag behind due to the non-homogeneity of the magnetic field. So you get sort of this fanning out phenomenon, this dephasing phenomenon, as sometimes it is also called. And and so we call that the T2 star process. Remember, that is because the field is not perfectly homogeneous. Okay, and so we have some of the fast ones getting ahead and the slow ones falling behind the pack, if you will. Okay, so the signal then starts decaying away experimentally. What can we do to reverse that? Well, the solution is actually pretty ingenious. It's also quite simple. What you want to do is to introduce the B1 again. Remember, there is no B1 anymore here or here, but now we bring the B1 field back. But we're going to keep that pulse on for twice as long to produce a pi pulse. Right, so here's my B field, my B1 field. It is oriented in the XY plane. As we'll see here, it will also be a rotating field. Okay, so this B field, this B1 field that we're now introducing at a later time will also rotate with the spins. So from the rotating frame of reference, it sort of appears static. The spins also appear sort of static as well in that frame. Okay, and so in that rotating frame, this picture here is pretty much static, right? So of course in the laboratory frame, everything is revolving around the z-axis. But in this rotating frame, we basically get more or less this static picture. But one thing will happen now to the spins in that frame, namely, they will start precessing about B1. Okay. That's what magnetic fields do to spins, right? They make them precess. And so that's what will happen now. These spins will precess about the B1 axis. So they will rotate about the B1 axis. What angle? Through what angle will they rotate? Well, it is a pi pulse after all. And so it stands to reason that the angle through which they rotate is 180 degrees, right? And so if this is the picture at the start of the pi pulse, so just before we turn on that pulse, that B1, the rotating B1 field, then the picture looks more like this after the pi pulse or at the end of the pi pulse, right? So every single spin will have sort of rotated by 180 degrees. And so picture this spin here rotating by 180 degrees about B1. Where does it end up? Well, it ends up on the sort of on the left of this here, of this picture. So 1 is pointing maybe somewhere here. 5, meanwhile, has rotated 180 degrees over to here, and now appears on the left. 3 hasn't done anything because B1 was sort of aligned with the third spin. 2, though, is now over here, and 4 is here. So the upshot now is that the fastest spin initially was ahead because, hey, it was the fastest. Okay, but after, at the end of the pi pulse, the slowest spin, namely the first one, is now ahead. When I say ahead, everything in the laboratory frame is, of course, processing clockwise here. Okay, so that's why we can use the term ahead or leading and lagging. So the upshot is that after the pi pulse, sort of the ordering of the spins in phase has been reversed. The ones that were ahead are now behind, and the ones that were behind are now ahead. Okay, the fastest one is lagging, and the slowest one is leading. And so you can kind of see where this is all headed. Right, the fastest one is now lagging, but since it is the fastest one, it will start catching up again. And the slowest one is leading, but since it is the slowest one, it will start falling back behind. And so you can sort of see how all these spins will come back together at some point in time. And the question then is, how long would it take for these spins to come back together in phase? And the answer is actually also not that surprising. It's going to take as long as it took them initially to come out of phase, namely to disperse. So as long as it took them to disperse is the same amount of time that it now will take them to recombine. Okay, so here's sort of a time axis now. We start with a pi/2 pulse. That gets us going. That gets everything started, right? That flips all of these spins down into the XY plane, and we get this FID as a result. But then that FID vanishes after a certain amount of time, and we now hit the system with a pi pulse, so a pulse of twice the duration. And then we have to wait a little while longer before these individual spins sort of come back together and reconstitute the signal. So here is what we call the echo. It's just a name that got attached to that. I guess it's the echo to the initial free induction decay signal. Okay, now just to reiterate here, we start at the end of the pi/2 pulse, everything is perfectly synchronized. Then after that, we get this period of dephasing until we hit it with a pi pulse where you get this reversal. And then you get a period where the spins come back into phase, sort of rephasing, I guess, if you will. And then, of course, they start dephasing again. Okay. And so this time between the FID and its echo, we can call, oftentimes it's called T sub TE in our text. We'll definitely refer to it as TE. Okay, so the question now that's quite important for us to contemplate is the following: is the height of the echo the same as that of the original FID? Now, echoes tend to be not quite as loud as the original pulse or the original sound, and so it is here as well. The echo will not be quite as loud, or the signal will not be quite as strong as it was initially. Because the answer is no here, and the question is why. Why does the echo height or the strength of the echo diminish with time? Okay, so that's actually what we see is that this TE, so the time separation between the FID and the echo, determines how loud that echo will be in the end. Okay, and so maybe not super surprising that if TE gets very long, then the echo actually diminishes quite a bit. But why is that? Well, we have the T2 process to blame for that. So it just so happens, for quantum mechanical reasons, that the T2 process cannot be reversed by a pi pulse. So that type of dephasing due to be local, the chemical shift, since that's quantum mechanical and microscopic in origin, you cannot reverse it using a pi pulse. You can reverse the sort of magnet inhomogeneity, but you cannot reverse the T2 process. And so that will sort of stay with us, right? So T2 phasing due to be local, it's a chemical shift, and it's quantum mechanical in nature, will not be able to reverse that. And so here's my initial FID, here's the echo. Now, of course, you could, once we get this dephasing again, you could hit the whole system with another pi pulse, trying to get another echo, the echo of the echo, if you will. Okay, and then that second echo would be smaller again. And so you get sort of this overall exponential decay envelope governing successive echoes. And so we see here, we get another type of decay, and it has its own time constant associated with it. We call that time constant T2. So that's the time it would take for the strength or the height of that echo to diminish by a factor of E. Okay? And so here, of course, we had 2 pi pulse. Now, we could also do this with just a single pi pulse, where we just sort of vary the time, the T sub E, or TE rather. Okay? We could just stretch TE out and just look at a single echo and its height depending on where it appears on the time axis. And actually, that is what we will do in the experiment. Okay, so hopefully now you've gotten some kind of sense of what T2 star is, what T2 is, what that sort of refers to physically. Okay, so we've discussed it at least. I hope that sort of made some sense, but you probably guessed that that's not the end of the story. There is one more important process that we need to discuss next. Right, so we've used the subscript 2 here. What about the subscript 1? Well, that is also a real thing. We call it T1 process or T1 relaxation. Okay, so with the T2s, basically what we get is that the individual spins remain in the XY plane. There's just a sort of a dephasing happening. Right, so there is sort of a fanning out within the XY plane of individual mu's. But they do not return to the ground state, namely, they do not sort of tilt back up towards the z-axis. But the T1 process returns the spin to their ground state. It does exactly that. It starts sort of moving, spins back in alignment with the big static magnetic field B naught. So we get this sort of gradual motion back towards the towards the z-axis. Okay, so this is what I want to illustrate here. Okay, initially, after the pi/2 pulse, we have this kind of picture, and then after some time, the mu's do find a way back towards their ground state. Okay, and it gets this gradual motion back towards the ground state, which is alignment with the z-axis. Now, of course, all the while, we also get this fast motion around the z-axis, this precession around the z-axis. Okay, so clearly the energy of the spins then decreases because, as you probably remember, we have this formula of U is equal to minus mu dot B. And so if mu aligns with B naught, and we can lower the energy. So as we're sort of tilting back to towards the z-axis, the energy, or the potential energy, if you will, of each of the spins decreases. And since overall energy has to be conserved, we have to find a way for that energy to be dissipated somewhere else. This energy has to go somewhere. Right, so when I drop a pin, okay, the potential energy goes down, but what else picks up the difference? Well, kinetic energy increases, right, to make up for the decreasing potential energy. Here we also have to find a way of sort of giving the energies to in some other form. Okay, and so the energy has to be dissipated, we could say, out of the spin system into some other degree of freedom. And so this takes time, simply. It doesn't happen right away. Typically actually takes longer than the T2 process. So then we have sort of this ordering in time. We have that T1 is the longest, then comes T2, and then and the shortest one is T2 star, as we discussed. All right, so the question then is, experimentally, how can we measure T1? How can we actually even establish it as an independent process from the other two? Well, there's a fairly clever method here that's called the inversion recovery method, one that we will also do experimentally. Okay, so instead of starting here with a pi/2 pulse to get things going, here we now start with a pi pulse. So right off the bat, we're doing something different, right? When you start off with a pi pulse, you're not tilting the spins down into the XY plane. Now you're gonna basically reverse the spin so that they now point against the z-axis. So yeah, this will flip them by 180 degrees. And so now they point against the z-axis. If they pointed up before, then now they point down. And so we would not expect a free induction decay to be produced. Because if these spins point against the z-axis, again, there's no precessional motion, no FID being induced in our pickup coil. We would not expect a signal. And this is actually one of the ways in which we can be sure that we've actually supplied a pi pulse experimentally, is if we don't see a subsequent signal. Okay. And now, once we've done the pi pulse, now we want to follow up with a pi/2 pulse. So in this inversion recovery method, we sort of reverse the order of the two spins. Sorry, the pulses, I should say. So we bring the pi pulse in first and then follow up with a pi/2 pulse, as shown here. So at the end of the first pulse, the pi pulse, we said that the spins were now pointing down, all of them. Okay. And so then if there is this T1 process happening, we wait a little while. Well, then at the beginning of this pi/2 pulse, they will have already maybe tilted back to their lower energy configuration. Okay, there's already, classically speaking, there's already been some attempt at getting back to the ground state. And so the longer we wait, in other words, the longer the separation between these two pulses, the more progress these individual spins may have made in their attempt to get back to the ground state. But now we're hitting it with the pi/2 pulse. So what happens there? Well, we get a further rotation. Right, we get a further rotation, and here by 90 degrees. So if this is what I've tried to indicate here, if this is sort of pointing diagonally down, then this is probably going to be pointing diagonally up after the pi/2 pulse. And so now we get a partial free induction decay signal here, right? Because we get this precessional motion here that we can pick up. Okay. And so the independent variable will be this separation in time, this delta t. Question is, what role does delta t play? Okay, so we're going to observe the strength of this free induction decay signal right after the pi/2 pulse. We're going to observe that as the dependent variable, and with the independent variable thing that we're going to vary is delta t. The question then is, what would you expect that relationship to look like? Okay, think about that for a moment. What might you expect that relationship to look like? Okay. So we're keeping track of the strength of the FID signal right after the pi/2 pulse, and we're doing this as a function of delta t. So when delta t is pretty much 0, right, then the pi pulse and the pi/2 pulse, those two pulses are very close together. There's not enough time for these spins to have tilted away from the -z direction. Okay, and so you would expect a fairly strong FID signal. Here, I'm going to account also for phase as well. So it's, this signal, I can count negative and positive depending on what the phase of the signal is, but that's a minor detail. We'd expect a fairly strong signal here, but then as we increase that temporal separation between the two pulses, then we get sort of, we'd expect really a reduction in that signal. We would actually expect that signal to go away completely. Okay. Here, we've basically waited a long enough time, sufficiently long time for these spins to have gone from the -z axis back to the xy plane, and then we're hitting those spins with another pi/2 pulse. Well, then they get rotated back to the +z axis, and we wouldn't expect an FID signal there. So upon a pi/2 pulse, they're then aligned with the +z axis, and so we should not get an FID anymore. Okay, so that is sort of what happens here. But then, of course, if you give the spins even more time, well, then they will now be above the xy plane, Okay, now you're hitting it again with a pi/2 pulse, and now you're going to overshoot the plus z-axis, and we should then get an FID signal again. And so we're sort of crossing through here the time axis and emerge on the other side. And the reason this is positive versus this is negative just has to do with phase. So you could also just plot the absolute value of this signal if you wished. Okay, and so we will do this inversion recovery experiment in due time. So this inversion recovery method basically tells you what T1 is, right? Basically, you just have to locate this point here. Where does the FID signal actually vanish? How long do you have to wait? All right. So just to give you a little preview, we're going to do that, but just to give you a little preview, we can run this experiment with different samples. One sample would be distilled water. So highly purified water. Okay, we have H2O, obviously. The H here, okay, is what we're sensitive to. We're sensitive to the proton. So the hydrogen nucleus. And for this sample, we get a T1 that is on the order of 1 minute, which is actually a very, very long time, especially when you compare it to, say, T2 star, which is on the order of 10 microseconds. So what's the difference here, right? This is 10 to the minus 5 seconds on the order of, this is 1 minute, that's like 60 seconds. So you get almost a factor of 10 to the 7 difference here. So we can say that 1 minute is almost like an eternity. So what that points to is that it is simply difficult for the spins to dissipate energy. There's nowhere for this energy to go in one sense, just because the sample is very pure. Okay, and but we can repeat the experiment with sort of water that has some impurity in it. So one thing you can do is you can dissolve sort of some copper compound in water. Okay, so it's actually dissolved. So you have like these copper ions running around in the water. Copper ions tend to be very magnetic. So what that means is they have themselves a fairly large magnetic moment that they carry around. Okay, and so now we might see how energy can be transferred out of the excited hydrogen nuclei. Maybe if they collide with the copper, in that collision, some energy can be transferred from one spin into another spin. So from the spin of the hydrogen to the spin of the copper. You can kind of see how now you sort of created a pathway for energy dissipation. It's interesting because you can repeat that experiment also with other salts that are dissolved in water where the ions are non-magnetic. And there you don't see this effect. You don't see this effect nearly as dramatic. Okay, here, it doesn't take very much copper sulfate to bring this T1 down from 1 minute into, into basically a regime that is on the order of T2, in fact. Even just a small concentration of magnetic impurity ions can dramatically affect the T1. And that's what we'll see as well in the experiment. So it's a nice way of measuring sort of the purity of water. If you have a way of measuring T1 it is very sensitive to that. And yes, so we will see how this T1 gets much reduced in the presence of these impurity ions. Okay, so we're almost through this last lecture here. We don't really have time today to get into MRI, but it is actually a really fascinating journey to go from what we've learned so far, pulsed NMR, to MRI. The one thing that's missing now, when we talk about MRI, the one thing that we haven't talked about is the eye part, the imaging part of it. We've talked about magnetic resonance plenty, but we haven't quite tackled the eye. So just very quickly now to wrap up this topic, MRI relies really crucially and centrally on the detection of these echo signals. So we're going to very much utilize these echoes to our advantage in MRI, but we'll also in MRI be very concerned with their spectral composition. So we're going to do a sort of a fast Fourier transform on these echo signals to see how they are, what their spectral composition is. So there's one more thing that we need, one more big thing, one more central thing that we don't need for NMR, but we do need for MRI, and that is the addition of field gradients. So in pulsed NMR, you can get away with a static field B naught, as we said, and an oscillating field B1 that you introduce at certain times. So this comes in pulses here, this B1, but B naught is static and constant. So that is sufficient for NMR. But if you want to get an image out, if you want to have some kind of spatial resolution, okay, then you need to, in addition to that, introduce field gradients. So the static field cannot be fully static. It'll have to vary spatially. And the first thing that you would do in MRI is to introduce a gradient along the Z axis. Then when you observe the FID signal, the frequency depends on where you are, okay, what your Z coordinate is. Then when you do a spectral, spectral analysis, you find that different frequencies actually now originate from different Z coordinates. So you've sort of resolved things along the Z axis. Similar things happen now also along X and Y as well. So we need these field gradients that sort of turn on and off at various times along Z, along X, and along Y. That actually explains the loud clanging noises that you hear when you're inside that MRI tube. So if you've ever had an MRI done, I think they give you like these headphones, right, to shield you a little bit from the loud noises. The loud noises come from the turning on and off of these gradient coils. So unfortunately, we won't have more time now to get into that. It's a fascinating topic, but maybe in a future lecture we can cover that. I think we've covered enough for today. Thank you for your attention, and see you later.